Okay, so welcome back, and today we're going to continue on with complex numbers, but we're now going to get into talking about what we call the trigonometric form of complex numbers. So, before we can talk about what the trigonometric form looks like and how it's derived, let's talk about the absolute value of a complex number. So, the absolute value, by definition, of a complex number is its distance from the origin. So we talked about how to graph a complex number on the imaginary plane, okay? So with that in mind, we define that the absolute value of that is going to be the distance that complex number is from the origin. And so this is how we define it then. So z, which is given by this complex number, so let's say z is a complex number in standard form, a plus bi, and the absolute value of that is, again, because the absolute value is the distance that point is from the origin, then it makes sense that it's just going to be the square root, using the distance formula, of a squared plus b squared, okay? Since the origin is 0, 0, then we just get a squared, right? So this is in the x direction. This b is in the y direction, so we get a squared plus b squared, and we take the square root of that, and that gives us the distance from the origin. Okay, now, with that in mind, now that we know how that's defined, what is the trigonometric form? Well, the trigonometric form of a complex number, okay, so for example, z equals a plus bi, the trigonometric form of z is given by this. R times the quantity cosine theta plus I sine theta. And the way this is derived is really straightforward. It's very simple, okay? Because it's the same way we would transform if we were looking at converting an xy coordinate into polar notation, okay? So with theta and r, okay? All we're going to do is we're going to represent a plus bi using theta and r. Okay, so what is cosine theta? Well, cosine theta is what? Adjacent over hypotenuse. And so in this case, what is adjacent over hypotenuse? Well, I've got my triangle, so here's a point. Here's the imaginary plane. I've got my point AB, right? And so now I'm representing this ray from the origin to the point, and I've got my distance in the x, a, and I've got my vertical distance, b. And so I've got this right triangle with an angle, terminal angle of theta, right? And of course the radius is r. And so now a, so if I go cosine theta, that's going to be adjacent over hypotenuse, so cosine theta. Okay, so cosine theta equals a over r, which means a, right? So that means a equals r cosine theta. So there's my first substitution. And then sine theta is opposite over hypotenuse, so that's b over r. And so that gives me that b equals r. Now, since this is I, since there's an I in there, I'm going to put the I, so it's r times I sine theta. So b, right? Oh, hold on a second. Let me get rid of the I. I'm getting ahead of myself. R sine theta. Okay, so now I've got what my A equals and what my B equals, and so I just substitute. So I'm going to get R sine theta here, and then B is going to be R cosine theta here, and B is R sine theta. And I've got the I here, and then of course all I have to do is rearrange the I and the sine theta and factor out the R, and I've got the result, and that's it. So, now, what about r? Well, r, as you can see, is the distance that this point is from where? The origin. Well, then r is nothing more than this. It's the absolute value of z, right? So that's r. So r is just the square root of a squared plus b squared. Okay, so what do we call that? So r is called the modulus. So just so you have some terminology here. So r is called the modulus. Okay? And theta is called the argument, of course. And that should be obvious because that's what we normally call theta. Or any variable that's going into the function. So again, this would be the argument. So theta is called the argument. Okay? Okay, so what can I do? Okay, now, so it's easy to derive. So if you ever forget, okay, what was that, what was the trigonometric form? Well, very easy. You could just use what I just did and easily derive the trigonometric form very quickly. Okay, I think it's, if you memorize it, great, then that saves you some time. But again, if you forget, just remember, I'm just using the right triangle and the ray and just using trigonometry to transform it into the trigonometric form. Okay, we'll come back and we'll do some examples next time.